Hi, this is Raj Singh from the Spanovation Bridge and Seismic School, presenting the basics of prestressing. So this is intended to be a high-level introduction to prestressing. Here are the topics that we will cover in this chapter. I'll first start with the purpose of this technology and how it works. Then we'll look into the two main types of prestressing options and how they differ from each other. Then, using the example of a simple prismatic beam, we will derive how prestressing produces an internal stress state that counteracts demands from external loads. We will understand the concepts of decompression moment and cracking moment. And finally, review the qualitative changes in stress state as the external loading increases, before concluding with the pros and cons of this technology. All right, so let's begin with the definition of prestressing. So prestressing is a process by which a concrete element is compressed by tensioning against a material which has high tensile capacity. So for example, right now I'm pre-compressing this blob of concrete with a high tensile material. And let's assume the force in this material is T, then my concrete is going to get an equal and opposite compressive stress, the resultant of which is going to be equal to the force T. So C would be equal to T. And how does this help us? How does introducing this precompression help us? Well, it helps us in increasing the load carrying capacity of concrete. And how does it work? Well, we all know that the weakness of concrete is tension. So prestressing works by counteracting the tensile stresses introduced by external loads. And the intent of prestressing is to eliminate tensile stresses in concrete and to generally keep it under compression. For example, if I were to take the same blob and to hang it upside down, anchor it to a ceiling, and apply a force T to it, we know that concrete really sucks in tension, so it's going to crack. And if this T force exceeds the cracking strength of concrete, we're going to have a large failure, and this whole blob is going to come falling down, right? But then if I instead use the piece of concrete that I just pre-compressed earlier with that tendon, sorry, it's showing up crooked, assume it's straight, then this already has a pre-compressive force C equal to T in it. Now if I apply an external load of T, then the concrete is just going to be in a state of zero stress, which means still no cracking. So on the one hand, I've got the same piece of concrete that doesn't even crack, whereas the first one's gone to failure. So this is how prestressing works. So there are two types of prestressing technologies available in the industry, commonly speaking. They're pre-tensioning and post-tensioning. So pre-tensioning is the process where the tendons are stressed prior to the casting of the surrounding concrete. So let's examine that first. So you're looking at a precasting bed and a precasting yard in that illustration. And the first step for pre-tensioning would be to stress your tendon, which in this case could be, let's say, high strength strands, but let's call it tendons. So the first step would be to stress these guys against the precasting bed. As you can see over here, there is no concrete to a certain pre-specified force, and it's reacting against this anchor plate, which is reacting against the bed. So after these strings, almost like the strings of a guitar, are fully tensioned, then you would cast your concrete beam around it. Of course, wait for the concrete beam to gain a certain strength. At that point, the strands or the tendons get bonded to the beam also. And then the strands are released at the ends, and that process then transfers the force through the bonding of the strands into the concrete beam. And at the end of the day, you've got an element which has a tendon running through it with a certain force T and an equal and opposite force, compressive force within your concrete. And this is how the pre-stressing is achieved in pre-tensioning. And of course, all this happens under controlled factory conditions in a precasting yard. Now, with post-tensioning, the process is a bit different. In this case, the tendons are stressed after the casting of the surrounding concrete. Okay, so you would still cast the beam in a precasting yard. However, it only has a void, or if you will, a duct. And this duct will house the future PT at a certain stage. It also has these pockets at the end for the anchorages. And after the concrete beam gains a certain strength, and generally actually occurs quite some time after that, because post-tensioning is mostly used to splice smaller concrete elements out in the field. Anyways, you would run your high strength material, let's say strands, through this duct, and then you would stress it. In this case, one end is the dead end, which is just anchored, and then the other end is where you're stressing against. So let's say a theoretical force P, and you're reacting against the beam itself. So when that process is complete, it's actually quite similar to the pre-tensioning process. You've got the tendon carrying a certain force T and an equal and opposing force, compressive force C, producing compression within your concrete beam. So these are the two common processes of pre-stressing. Now, the one thing to keep in mind over here is that post-tensioning does offer you more flexibility in the geometry of your tendons, because you do have the ability to achieve more complex geometrical shapes with your ducts and then weave your high strength material afterwards and post-tension it, compared to pre-stressing, because it is more difficult to achieve complex geometries with no concrete and just high strength strands, if you will. So we know that the intent of pre-stressing is to eliminate tensile stresses in concrete as best possible. And it does so by producing a state of internal stress that counteracts the stresses produced by external loading. For example, in the case of a simply supported beam that you see on your screen, the bending moment diagram follows a parabolic shape with the maximum moment occurring at midspan and moments at the ends reducing to zero. So if you were to examine three sections, let's just start with the section at the end and call it section AA. So over here, my tendon doesn't need to have any eccentricity from the neutral axis because the bending moment is zero. And as we move on and go to the quarter point, somewhere over here, let's call that B, section B. You can see that my moment demand has increased, and so has my eccentricity, which tends to produce an opposing or a counteracting moment to balance the applied moments. And then as you get to midspan, let's call that C, section CC is where I have the most or the maximum eccentricity to counteract the externally applied moments. So this is how you could give your tendon a profile to suit the demand envelope to best counteract it and nullify tension in concrete. Although it's not always practical to do that, but theoretically you could. Okay, so on this slide, we're going to examine the internal forces from pre-stressing. What you see on your screen is a simply supported beam that's been pre-stressed with a draped tendon, which has zero eccentricity at the ends over here, and that keeps increasing. And at midspan, you've got the maximum eccentricity of the tendon from the neutral axis. Okay, so to develop the state of internal forces, and I'm going to examine the section right at midspan over here. What I'll do is I'll look into a free body diagram of the left half of the beam, so slice it right in the middle, and notice that there is no external forces that are acting on this beam. So from the outside, the beam is perfectly in equilibrium. When I slice it is when I start seeing forces on the right face of the left half of the beam. So looking at those forces, there is of course this pull force coming from the tendon. Let me call that force P. And this force has to be perfectly in balance, or for equilibrium needs to be balanced by another force that's a reactive force between the two faces of concrete, between the left and the right face. And let me call that reactive force R. And this force has to be equal in magnitude and perfectly coincidental with the P force for this face to be in equilibrium. So knowing that, let's look at that piece of concrete a bit more closely. So I've just zoomed into that piece now over here. This is my neutral axis of this section. and here is my tendon, and the tendon is applying a pull force on this face, and that pull force is P, as I said. Now, what this does is, as it pulls this left portion of the beam, it's pulling it against the right portion of the beam. So that's the right portion, and there's bearing between the two faces, and there's a whole bunch of little reactive compressive forces amongst them. And if I were to add all of these guys up, there would be this net compressive force, and that compressive force, or the reactive force, as I'd shown earlier, should be equal in magnitude to the force in the tendon, and it should be sitting exactly at the same location at eccentricity E. Knowing that this is the force, the internal force, internal compressive force at the face of concrete, what I can then do is I can resolve this force into two components. I can move this displaces force parallel to itself at the neutral axis, and that's not adequate, because then the section would not be in equilibrium. I also have to provide a net moment, which in this case would be a clockwise moment, so P times E applied to the section. So a combination of these two would be the equivalent of the force P acting at an eccentricity E. These are the two force effects I need to work with, and I'm going to use them on the next slide to develop the state of internal stresses from prestressing. Okay, so now let's look at the internal stresses due to prestressing at this concrete section right at midspan of the simply supported beam. On the previous slide, we realized that at this section there is a net compressive force P that's acting at the neutral axis, plus there is a clockwise moment that's being applied on the section. Those were the equivalent force effects we derived on the concrete section in the previous slide. So our approach to finding the stresses would be to convert these forces, or to derive stresses from these forces and then add them up to get the stress effects. Stress from the axial force is simply the axial force divided by the area of cross section. The section has, it's a rectangular section, height h, width b, so h times b would be the area. So the uniform compression that's applied by the axial force would be the axial force divided by the area. And compression is denoted by green. Now for moment, it's going to have a linear variation with tension on one extreme fiber and compression on the other, and going to zero through the neutral axis. Now, since our moment is a clockwise moment, it's going to lead to tension at the top of the beam and compression on the bottom of the section. And the value of that would be the moment divided by the section modulus, which, let's say for the bottom fiber is SB, and for the top fiber is ST. I'm also going to call tensile stresses as a negative, so that would be the moment divided by the section modulus of the top fiber, that would be ST. Now if I were to add these two stresses, I would get the net stress due to prestressing. So on the top, it would be the compressive stress from axial compression minus the tensile stress from moment. So the net of that would be the stress on the top fiber. And similarly on the bottom, it's going to be P divided by A plus the moment P dot E divided by SB. So what we're seeing in this case is generally we end up with a large compression on the bottom fiber and a smaller compression on the top. And if you just study the quality of the state of stress, this is something that actually tends to negate the stresses produced by external moment, because remember, on a simply supported beam, an external uniformly distributed load or even a point load would produce an effect that would create tension on the bottom and compression on the top. So the quality of the stress profile is something that tends to oppose the stresses produced by external loads. Okay, so after all that theory, let's do a fun exercise. So it looks like we've got a question over here. It says, what is the maximum eccentricity that can be provided without causing tension in the top fiber of the beam section due to prestressing? Then it goes on to say that ignore the self-weight of the beam and assume the neutral axis is at h/2, or right at mid-height of the section. So in order to do that, let's focus on the top fiber of this beam. So just focus right here. And we know that the force effects from pre-stressing are an axial force acting at the neutral axis and a moment, which is the axial force times an eccentricity E. So as we've done previously, let's develop the stresses due to these force effects in the top fiber. So the top fiber is going to see a uniform, well, the whole section is going to see uniform compression from the axial force. And that compression is going to be P divided by the area A. And then from the moment, we're going to see stress in the top fiber, which is a negative stress because it's tension, which is the moment divided by the section modulus of the top fiber. Now, if I were to add these two, we should get the stress, overall stress due to pre-stressing. And for the top fiber, that expression would be this. For us to ensure that the top fiber does not go into tension, the limit would be when this stress is equal to 0. So this is what we need to work with. Now, the other thing it says is that the neutral axis is at mid-height, which is right in the middle of the concrete section, which means the top and the bottom fibers are equidistant from the neutral axis, which means ST would be equal to SB. The section modulus with respect to the top and the bottom would be equal to S. And I know that for a rectangular section, it is B, which is the width, times H square divided by 6. Okay, so you can go check this expression out. You can Google search it or go to any textbook and you should be able to find it. I'm going to use this equation over here. Let me call this equation 1. And I'm going to use the section modulus. Let me just call this 2 and work with these two guys. So I'll take, let me take P out as common and divided by the area, which is H times B, minus the eccentricity E divided by the section modulus, which is BH square, and the 6 goes to the top, and this whole expression should be equal to 0. Now I can just cancel P out, and now what I'll do is I'll solve for E. So 6 times E divided by BH square should be equal to 1 by HB. B cancel on the two sides. I can cancel one of the H's out, and this gives me E is equal to H over 6. So that's what the eccentricity needs to be right at the limit of when the top fiber wants to go to tension. So it's right at that balance point where the stress is 0. So if the E eccentricity were to get greater than H over 6, then pre-stressing would start producing tension in the top fiber. Right, so now let's evaluate the effect of external loading on the simply supported beam. Of course, those loads come in from dead loads and live loads. And let's assume that there is an external moment M that's applied to this cross section, which is right at midspan of the beam. So the way we look at that is it's a simple superimposition of the stresses produced by pre-stressing. I've derived the expressions for the stress in the top and the bottom fiber previously. And we superimpose those stresses with the stresses coming in from this external moment M. So at the top fiber, that would be M divided by the section modulus to the top. And on the bottom, it would be a negative since it's a tensile stress, M divided by SB. And simply adding those expressions together would give us the net stress. Just to quickly review the stresses due to an externally applied moment on a simply supported beam is going to give you compression on the top fiber, tension on the bottom fiber, sort of the opposite of the effect that pre-stressing would produce, and thereby in the net stress diagram you have lesser compression on the bottom and greater compression on the top. Okay, so now we'll introduce the concept of the decompression moment, which is the external moment at which the stress at the bottom of the beam becomes zero. So we know that the net stress state on the beam are a combination of the stresses coming from the prestressing plus the stresses coming from the external moment M. And the stresses coming from prestressing are a combination of the axial component plus the moment due to the eccentricity of the tendon. And the stresses on the bottom coming from moment would be the moment divided by the section modulus at the bottom. And I'll put a negative sign to denote tension. So we know that this on the previous slide. So the addition of these two would give you the net stress state. Now what the decompression moment means is that as the external moment keeps increasing, or in other words, as this stress from the external moment keeps increasing, then the stress in the bottom fiber keeps reducing. At one point, the stress of the bottom fiber is going to go to zero. And that state is defined as the decompression moment. Okay, so if that is clear, then we can move on to the next step over here, which is asking us to calculate the expression for decompression moment when the eccentricity is h/6, as noted, and assume the neutral axis is at h/2. So let me just quickly write this down. E is equal to h/6. The implication of the second assumption is that the section modulus of the bottom becomes equal to the top is equal to S, and that we know for a rectangular section would be bh²/6. Okay. To calculate the decompression moment, what we've got to do is we've got to set this expression for the net stress of the bottom fiber equal to 0. So let's do that. And just to create a bit more space for us, I'm gonna use the eraser over here and get rid of these guys and quickly write that expression again. So sigma bottom is equal to P by A plus P times E divided by S minus M over S is equal to 0. Solving for M and rearranging things a little bit, let's say M over S. Taking P out common from the expression, 1 over A plus E over S. Next step, I'm going to multiply both the sides by S, so I'm left with M alone on the left-hand side. And on the other side, I've got P S over A plus E times S divided by S, which is great, cancels out. Now I can start introducing the parameters. So S, as we can see over here, is bh²/6 divided by the area, and area would be the height times the width, height times the width, plus eccentricity, as we noted earlier, is h/6. There's a whole bunch of things we can cancel out over here. We can cancel out b, we can cancel out one of the h's, and I've got h/6 plus h/6, that gives me ph/3. So the decompression moment, the expression for that would be ph/6. In other words, when the moment from the externally applied loads becomes equal to the tendon force times the height of the section divided by 3, then the stress in the bottom fiber would go to 0. So now let's look at the cracking moment. So cracking moment is defined as the external moment at which the stress at the bottom of the beam equals the cracking strength of concrete. So we know when we looked at the decompression moment that the stress in the bottom fiber continues to decrease as the external moment keeps increasing, and eventually you get to a state of zero stress. The moment that produces that is called the decompression moment. Now, as the stress continues to decrease and the section gets into tension, at one point the stress on the bottom fiber would become equal to the cracking stress of concrete. So the moment that produces that stress state is known as the cracking moment. So in this slide, we'll review the qualitative changes in the stress diagram with increasing external moment. Previously, we've looked at what the stress diagram looks like under pre-stress only. And just qualitatively, it's got a high compressive stress on the bottom fiber, a much smaller compressive stress on the top. And the reason for that is due to the eccentricity of the pre-stressing from the neutral axis. And we're looking at this section at the midspan of the simply supported beam, so it's got maximum eccentricity over there. So again, just to quickly review the concept, it's got a axial component that produces uniform compression, and it's got a moment component, which is that axial force times the eccentricity that produces a higher compression on the bottom and a tension on the top, and the summation of both of those gives us this quality. Now, let me just quickly switch to a marker mode so I can draw something. The other thing is the stress line of a stress diagram is this, the front line over here, this one. And you'll notice that as the external moments are increased, this line would pivot about the neutral axis. So this is the pivot point. So let's start. So as we start increasing external loads, let's say we activate the self-weight and start adding dead load, what you'll find is that the top fiber stress starts to increase, there's more compression in the top, and the bottom starts to decrease. At one point, you'll get to a state known as the balancing moment. No points for really guessing that, but what happens in this state is that the external moment goes to a value that it fully nullifies the moment component of pre-stressing, which is coming from the eccentricity of the tendon. So when that gets fully compensated, you've got a state of pure compression that's simply the axial pre-stressing force divided by the area of the section. So that would be the compressive stress. So then moving forward, the external moment continues to increase, and you can see the further pivot in a clockwise direction of this stress line. And then it further pivots. This gets to a state now where the stress in the bottom fiber goes to zero. And we've looked at this previously. The moment that produces that is called the decompression moment. External moment that leads to a state of zero stress in the bottom fiber. And then as we further increase the moment, again, you'll notice the pivot about the neutral axis of the stress line. The bottom fiber goes into tension, and eventually it reaches a stress that's equal to the cracking stress in concrete. And that, of course, is called the cracking moment. That's really how, qualitatively, with increasing external moments, the stress diagram changes. So we've gone through some of the basics of pre-stressing, and now it's time to end this chapter with a quick pros and cons statement. So one of the big pros for me with regard to pre-stressing is the elimination of tensile forces in concrete and keeping the section generally under compression. And of course, we've seen that it does that by the application of pre-compression through the tendons. The big advantage that that brings is that it allows the entire section to participate in load resistance. So if you contrast that to a regular girder that under service cracks, so the section below the neutral axis does not really participate in any load resistance, but you're still carrying the dead load of that in a regular beam. Whereas on a pre-stressed girder, your entire section participates in resisting the payload. So thereby you're able to span longer distances for the same section depth in a pre-stressed girder compared to an unpre-stressed girder. The other advantage, of course, is the enhanced durability due to elimination of cracks. Now on the con side, it is greater costs to manufacture pre-stressed concrete because it does require a specialized setup, a precasting yard, and also specialized equipment, whether you're doing pre-tensioning or post-tensioning. It requires people that know what they're doing. So it does require a certain level of skill and, of course, more complex processes and quality control processes to manufacture relative to plain reinforced concrete. In conclusion, you can say that pre-stressed concrete starts to gain an advantage when the higher cost of its production compared to reinforced concrete is offset by the economics of its material efficiency and long-term durability.